Yeah, so welcome to TGLF, where we check out a machine learning paper every month and just talk about it. We're going to share our impressions, go into each other's key points, and talk about what this unlocks for us as ML engineers and the industry as a whole. So, what was your first impression from the R1 paper?
For me, the demo was awesome. I tried R1 and it was showing me the think steps, all the internal thought process or the what do we call that? The inference time scaling steps. I have not seen models where I would pay attention to the internal steps. Sometimes we don't even get access to those, and even if we did, I would just skip over. But for this model, when I look at it, well, that sounds actually useful. I could see what it is working on. Sometimes it would say, I want to be respectful to the user. I want to be nice to the user. So all the things that was amazing. What was your first impression?
I think for me, it was how they used what at first looks like a noisy policy
Yeah.
by foregoing the value model. Seems like just an efficiency gain, but they were able to see it scale up its thinking process without really having an overbearing hand on how that thinking process should unfold. So it was really interesting to see as the training steps increased, its thinking process actually got larger, and they show an aha moment of it actually doing reflection tuning within itself without being explicitly, coded to do that. So, but then again, I mean, I'm I'm a noob when it comes to reinforcement learning. So I had to go into their old GRPO paper, and I'm still wondering how is the reward calculated? I mean, they show a little
I get you. Yeah.
how do they
We we have been hearing a lot of oral papers lately, and like haven't I haven't sat down to really get to the depth of the oral papers, but this time this paper was so interesting. I wanted to, okay, now we have seen enough interesting work. Now it's time for me to sit down and learn RL.
Yeah.
So, from what I learned, I can give you a quick overview. Sorry, let me quickly re-share my screen. So, I downloaded a bunch of RL papers. I'm not sure if you can see this.
Yeah, yeah.
So, so the first paper that comes to my mind when I see RL work is this reinforced paper. I tried to read this. This is from 1992, so it's like
Classic.
30 plus years. And the
It's older than both
thing
of us.
about this paper is it's long, 28 papers, 28 pages, but it's pretty sort of our deep learning works, right? It's 1992, and it goes in depth of discussing like how do we do the back propagation. Now we take that for granted. We just do something like PyTorch or anything that has auto graded. Just take it for granted. But here it goes in depth. How do we squash the neurons to 0 to 1, like the sigmoid functions? So it gets
Right.
into that, and then I was lost. So I couldn't get the big picture because I was lost with the details. But I think from my take, first important paper we should catch up is this TRPO from 2015.
Yeah. Yeah. The
So
online
this
gradient.
I wish I had seen this paper years ago. So this is from Schulman. I don't know if I'm saying his name correctly. So he went on to co-found OpenAI. So he's one of the co-founders, and he has written few papers on really groundational paper on RL. So this paper talks about the notations. For me, the most now there are like this is 2015, and then they write another paper in 2017, another paper. So, but this paper sets up the notation. So a lot of those equations we see, I was looking at what are these notation? Where are they even getting this from? And then only when I see this paper, oh, now that makes sense. So this one actually writes the notations.
Mm.
I'm not sure if they borrowed it from some other paper, but I haven't seen such depth description of notations in depth like this one. So there's a whole section on preliminaries where they talk about notation. And then, so this is TRPO, Trust Region Policy Optimization. Then that was 2015. The same author and with the new team goes on to write PPO. That's the popular one. I think we have seen this one. Proximal
Right.
policy optimization. So you recognize the same author. So they improve that model. And then we come to 2024, the GR pivot. This is from the DeepSeek authors. They take the P pivot, which we just saw, and then they revise it to GR pivot, which is what is used in the paper. So when we look at the paper, we just see this, we did this, but there is so much background info we need to fill to really understand what they're doing. So that has been my exploration after our previous chat. I've been, okay, let me try sit down and try to understand this. Yeah. So how was your exploration to Autumn in the past few weeks?
I pretty much was doing the same thing, but I still feel like a complete noob. And I kind of paused the R1 paper halfway through when I realized, oh, they use GRPO, so I want to like get into that.
Yeah.
And there's some interesting things that they do, like outcome scoring the reward based off of the outcome, and then scoring the reward based off of the process.
Yes.
I wish I had just finished the R1 paper first because they kind of show they answered the big questions which I had, which were they use a rule based reward for the big reasoning tasks, and
Yes.
then a generative reward for general data, only using the final summary. So that answered the big question that I had, like where does the reward come from? How do you really score that?
Yeah.
In the end, they show that they tried to reward the process with the R1 paper, but found that it gave meager gains for so much computational overhead.
Mm-hmm.
Also with Monte Carlo tree search, found that it just wasn't generalizing for at least like this large scale process. And I think what was like really impressive is that by having pretty, relaxed constraints on how the reward is generated, it started to exhibit, relatively complex behaviors like internal reflection tuning within its own first think output, you know? So, I mean, it's another big win just off of scaling.
Yeah. Yeah. So we saw in V3 paper they try to make the whole process efficient as possible. I
Yeah.
think the GRPO reward RL method is another take in the same direction. Took PPO and then they simplified it to make it more efficient. I think in this figure, or maybe we should take a overview first before we dive into it.
Yeah. Let's do this one.
If somebody's gonna watch us record this, maybe we should give them an overview. So from my takeaway from this is okay. So there are the paper I can divide it into three parts. The first part is the DeepSeek R1 0, which here we see section 2.2. Then they have the DeepSeek R1. R1 0 was required to get to R1. So they talk about R1 0, and then they get to R1. We can see that in detail. Then they have distillation three parts, right? But the first part, I think, is easy to understand. So let's dive into R1 0.
Yeah.
So from what okay, so I took some notes. Maybe I'll quickly share some notes so yeah, so here. So they take the V3 model, which we discussed in a previous chat. They take the V3 model and add a reinforcement learning to it, and then you get R1 0. Okay, so this was my take. So with this reinforcement learning method, what they are focusing on is something that is easy to evaluate. I mean that's another key factor. Sometimes evaluation, the reward model, building a reward model is hard for RL. It's that itself is hard. Once you have that, then you have to tune your models for maximizing that reward. But here they take a smart approach, which is let's pick the task where evaluating or computing the reward is easy. And
Yeah.
the task they picked is now I'm gonna jump back. Okay, they took so basically the for the R1 0 they have two rewards, two kinds of rewards. The first one is accuracy reward. So here they pick tasks like math problems where it's easy to evaluate and get to know whether the answer is correct or wrong. So it's easy to
Right.
evaluate. And then I think they also did a lead code problem. So where the verification is easy. So if the model generates code, say Python code, evaluate it, you have test cases for lead code. This is so I think that was one smart approach here because building a reward model is hard. So here you select a set of tasks where reward model is easy, then you evaluate it. And then the second reward they had is making sure the format of the response is correct. I think on this one they probably return some regex to make sure the format is right. So it's easy. So then they train the model. Right. So they have. So if you look at, so the key point here is the data sets. Right. The second reward is easy. You just have to probably write a regex to see whether it's passes or not. And the first one, data set for this is discussed in GRPO. So that's the whole thing about GRPO paper. I don't think it was called GRPO. It was called DeepSeek Math. So they
Yep.
talk in depth about creating a data set. Um, and then add GRPO, right? So they create a dataset and propose a method. So they already had good expertise in this direction where they can solve math problems, and they have their own custom dataset that they spend time creating it. I'm not sure lead code problem. I didn't. Probably there is
I
a
didn't.
way to use dataset.
Yeah, I think they embellished the DeepSeek Math data set to include leap code problems. The DeepSeek Math paper was mostly looking at like, okay, we have this coding model that was pre-trained on coding stuff, so that's probably where they had the leap code problems.
Yeah.
And then just train it on math problems. But the interesting finding that they had was that if they then applied that math reinforcement learning tuned 7 billion parameter model on coding problems, it did even better because it was able to
Yeah.
reason better. That was actually a really cool finding, which kind of suggests that it suggested to them that this reinforcement learning approach will actually have emergent properties. And that's what we saw in here.
Yeah. Then they compare with the OpenAI O1 model, I think. Before we get to evaluation, yeah. So then they train uh, this model and we get DeepSeek R1 and the performance is comparable to O1 or maybe Deep O1 Mini. I think the Mini is, when I'm looking at the name Mini, I'm not sure the internet is Mini, I assume they have distilled one. So that's the O1 model. I'm sorry, that's the R10 model. But I think as you pointed out in the beginning, as they increase the training steps, they start to observe that the response length also increases. So that means the model is spending more time in
In the
thinking
think
or
phase.
inference time scaling. And as the response length increases, I think they've also said somewhere maybe it was here. So there are two. I think we have to combine these two plots to get a bigger picture. So in this plot we see, so on the x-axis the time increases, and on the y-axis we see model is generating longer responses. That means it's spending more time in things steps. Probably more time. We don't know for sure. But and again we see the accuracy is also increasing. So in this plot, so they say this is what I think they want to achieve: the make a model that can do inference time scaling, so it can think or produce a lot of these steps and then give you the answer. And here we see they're reaching O1 performance or sometimes beating it. Yeah, that was they took week. So in summary, they took weekly model and they have their own expertise with the previous work on DeepSeek math work, where they have created a math data set and they have proposed a new method called the GRPO. They took PPO and then modified it, simplified it to make it a GRPO. And that when you apply on V3 model now, so the DeepSeek model was applied, this was before DeepSeek V3. Now they have a stronger base model. I think that's one important observation here. And they do the same thing with the few more addition on a stronger base model, which is V3. Now you have this magic happening, which is they are able to, they are able to compete with OpenAI 1. So now if you want to, so it looks like we have a so what are the key ingredients to make this a successful experiment? One, they have a stronger base model, which is the
Yeah.
V. Two, they have good data set. And three, they have improved RL method, or maybe, I don't know, when we say improved.
Free RL method, like basically instead of having to have two models
Yeah.
side by side, they just need to train that single one.
Yes. Um, how about we? So I can this equation when I looked at it, like, okay, these notations are all foreign to me. I need to spend more time understanding what does this even mean, because we don't see outside of RL, we don't use this notations. So I spent some time looking into what is the crux of this method. What are they even trying to do? So let's start with TRPO. This is a 2015 paper, 10 years ago. Can you believe it's a kid already? So this paper describes this RL objective where subject to maximizing some objectives subject to I should have highlighted that equation. So yeah, I think we have to look at this equation. So it has a maximization objective. Ignore this term for now, but the key thing is they add a constraint where KL divergence that has two terms. It should not be more than some hyperparameter delta.
Right.
So this is our objective, but it's not we are not free to maximize it however we want. I mean, in the sense it has to be under this constraint. That was the um, key takeaway from this paper. So the KL divergence basically now, if you want to dig a little bit deeper into these notations, I think so. I try to understand where are they getting this from. I think this is from this classic math model, which is a Markov decision process. There is a Wikipedia page for this. I think it even explains this start. So this is so the Markov decision process, where basically along the lines of HMMs we have seen. But this is we have states, we have actions, we have transition probabilities. So these are the notations that represent that model. So the pi function is a policy. I think the term pi I wanted to highlight is this is the policy we are trying to learn. The policy here, what state, given a state, what action the model should take. So we are and then we have rewards for that. I think, yeah, considering time, I don't think we can spend too much time in mutation.
Yeah.
High level takeaway here is this paper, it introduced this objective and then said K divergence. Well, one thing we know about K divergence is it has lower bound. K divergence cannot be negative. So we know it's bounded, lower bound is zero. But the higher bound, upper bound, there's no like fixed upper bound for K divergence. So it can be really large. It's ensuring that the model does not change too much within the outtakes. So that's main takeaway for me. Then 2 years later, they write this paper called PTO. And I think this went on to become the core part of ChatGPT because now you see the authors now OpenAI. And what do we know about this method? So the same equation, they took that same equation. So this was the TRPO method.
Right.
Now they replace this constraint with PPO, where they use a clip function, which seems like a smarter way of putting the constraint. Okay, so uh, again, we still didn't talk about what is this advantage function, and there's so many hyperparameters we didn't talk about. So that is PPO. Then the GRPO, what they're doing, they take PPO, and so now we see how we got the clip function. Initially, there was no clip function. We were just maximizing this objective under some KL divergence term. Then the PPO came and said remove the KL divergence and then instead use the clip function. And then the GRPO takes this to the next level. It looks like we introduced KL divergence, but here I think.
From what I understand, the Kale divergence wasn't mutually exclusive with the clip. The Kale divergence was basically finding a cutoff point on how to like escape how much you update the parameter or the model based off of your, the previous policy. Like at the PPO, you have, or the trusted region, you have, you know, a previous policy and then a new policy that you're iterating on. And you have to have some like break off point for this particular example on like when you want to stop updating the policy. And so the Kale divergence is like showing a time or like a point at which you no longer update your new policy on this example. Clip was another way. So that like allowed them to stabilize the reinforcement learning process.
Yeah.
Using the clip function, it was another way to stabilize the process so that it wouldn't change too much to maximize the advantage
I see.
for this particular set of examples.
I see.
But it's not mutually exclusive with the Kale
Oh,
divergence.
I see. So it's an additional constraint to stabilize the training.
Exactly.
Okay.
Yeah.
So now thank you. Now the simplification here is, I think if we look, they have used two colors to shade. Which one is the frozen, other one is the train model. I think the yellow is the train model. So they're trying to get rid of the value model, which I'm still having trouble understanding how the value model is used in these all the equations.
Yeah.
They just mentioned this term. This is a value model. I mean, I get to the high level, they're using another model to give a reward, or maybe I'm missing the whole thing.
Yeah, no, I don't. I think they show that you can use a model to get the reward, but what they actually do for this math stuff is, since it's a very clear right and wrong answer at the end,
Yeah,
they just use like an algorithmic function to define what the reward is.
I see.
And then to go from the reward to the advantage, they use a pretty simple algorithm, which is calculating the mean and the variance of the rewards in that group, and then adjusting the reward based off of the mean and variance, which is it seems like a really silly step, but such a simple step was allowed them to take away the value model, which oftentimes is as big as the policy model itself.
Yeah, that's another clever optimization. If you look at it, so they say a value model is often as big as the policy model, so they just get rid of that. They reduce the memory and compute constraint by getting rid of value model.
Yeah, and the
Although,
reference model is the state of the policy model before it started updating
yeah,
on the set.
I see. Yeah, that's unless you have more items to dig in the
Let me see if there's a couple more on the.
paper.
I honestly didn't really understand the implications of the full unified paradigm that they introduced in section 5.2. Sure, it was a big deal, but I didn't get it. It was a
Is
little.
it a R1 paper or is it a DeepSeek math paper?
It's in the DeepSeek math paper.
Math paper. Okay, yeah, you mentioned this. Like, if you first train on math problem and then do coding, the reasoning improves. In a way, they're saying if you're good at math, you may be good at coding, which is not system in CS at least.
Another, I think actually there's one piece of the GRPO paper, 5.2.2, why reinforcement learning works.
Point to point, I'm getting there. Okay.
Yeah, this part that they have in bold is really interesting. That reinforcement learning seems to boost the correctness of the top K responses rather than fundamentally changing the way that it thinks necessarily.
So what you're saying is it doesn't change which of those are actually top K, it just that makes top K separate from the rest. Is that what boosting means?
I think it's that instead of the model like discovering new methods of arriving at the answer, it just boosts the likelihood of generating good intermediate steps.
I see. If that's somehow related, I think it should be somehow related to the figure. I had skipped over this section. So this one is majority at K. This blue is RL, green is non-RL. Performance but not pass at K. Okay, then it's just majority at K but not pass at K. I see. I think yeah, that makes sense now. Okay.
So, like in the space of possible things that the model could have generated,
Yeah.
it just rises the useful answers to the top, which I guess makes sense. But I think that this finding makes their other finding in R10 all that much more impressive, where just with a pretty loose set of constraints on the RL process, the model is able to begin to do reflection tuning without ever having been instructed to do reflection tuning.
Okay. This. Okay, I think we have reached the end of the math paper.
Yeah,
Now
that's the math one.
let's get back to the R1 paper. Okay, so now we looked at take the base model. We took an overview of their RL method, and then we got DeepSeek R10. But their whole argument so far is that they didn't do any supervised fine tuning. So they didn't spend any time preparing instruction fine-tuned dataset and tuning on that dataset.
Right, for the R10.
Yes.
But then it was mixing languages and
Yeah. So they didn't show all the answers in math problems weren't towards aligning like it has to be nice, it has to be coherent. It was all about do you get the correct answer or not, right?
right.
So as a result, I think my understanding was when you actually look into this outputs, you see sometimes it could be doing so many things that human it's not useful for a human. If you put it as a chatbot, it might go from Chinese to English to Chinese to English.
Sounds possible for the DeepSeek team, but definitely not for us.
Right. So code switching was one of the problems they said. They wanted so when we use the R1 in an app, we saw the think steps were so coherent and useful for us. I could read it, and then, oh, I know what it is trying. If I ask any ambiguous question, it would say, does the question mean option A? Does it mean B? Maybe option B. So maybe I should clarify. All those thought processes were very coherent when I looked at least. I mean, it's not going to be 100% coherent, but majority of the time. It looks like R10 was not that because there was no alignment. They didn't create that data set where they show how to express the thoughts that is understandable or useful for a human. Then that's why they started working on R1, basically R1 instead of R1, from R10 to R1. So they talk about this cold start problem. So here, what they did, they used few shot counting on. So they took R10 and they generated some samples think directly prompting the models to generate a detailed answer, gathering DeepSeek R1 outputs in a readable format, and refining the result through post-processing by human. I think this was so they took the R1, asked the R1 to generate the think steps and answers, and then they sent it to humans to post-process it. So now we are spending human effort in correcting, in generating the output, in showing how to generate outputs. And this is the supervised fine-tuning step they talked about.
Right. It is interesting to me that the second step that you have highlighted there in that four-step creation of the supervised fine-tuning process, it's not. It doesn't really matter where which model made those steps or made those generated answers. You could use, any quality model that makes good enough answers. You could add to
You are
that.
touching a really
Sensitive
important and
topic.
very controversial topic. Some people
I
are
don't
saying,
know. I don't know.
they might have gotten it from company XYZ. I'm not gonna name who.
Yeah, yeah, but I mean, they have to generate all their thinking steps
Yeah,
themselves because that's the only way that they can get that. But actually getting the detailed answers that, go back to themselves, you can use any model that you want.
yeah, yeah. So it doesn't have to be R10. I guess having something of the same base model may be helpful, I think, but it doesn't have to be. It could be,
Pos-
considering this is along the direction of distillation, if you can have a stronger model to generate your samples, and then you refine using, you posted it using your human annotators,
Speaking
then
of
you're
which,
going to beat that strong
yeah,
model, whichever you sampled from.
can we jump to the distillation section, actually? I'm uh actually no, we can get to the distillation section afterwards.
Yeah,
Let's
yeah.
keep going.
So,
Let's
but
keep going.
the important thing is now cold start. The difference between R10 to R1 is this cold start step, right? And this cold start step, the main part of this cold start step is creating samples, good enough samples, and then post-editing from human. Now
Yeah,
there is a whole lot of debate going on. Like, are you sure you didn't use your competitors to this to generate the samples? We don't know. So we don't know. So if you
true,
take,
by the way. Yeah.
yeah, that's some people are very skeptical about this part because we don't have the access to data. We have to take their words for it. So I think, we there is research ethics sites. We write what we did, and this is what they have done. But this is why the media was going crazy. So maybe they are distilling some. Maybe they're not talking about all the places where they are getting the sample. So then I think they asked this step called rejection sampling. So they,
Once they have that new data set
yeah,
in section 2.3.1,
yes,
they fine tune DeepSeek V3 on that
yes,
using supervised fine tuning. And then they do the GRPO training process on the fine tuned DeepSeek V3
yes,
with the cold start data, and then basically create a new zero, but from the supervised tuning section,
correct.
which only has rule based rewards, and then they add an additional language consistency constraint to kind of get it closer to what a human would be able to read.
Yeah,
So based off of the primary language in the prompt, it has to stick to that language in the output.
yeah.
And then the rejection sampling, they
The newer R10 that had
exactly
cold
they
start.
take that and then generate more training data. They definitely generated it themselves,
Yes.
but in new domains like writing, role playing, and other general purpose
Yeah.
tasks. So now they have this new reasoning data, which has it allows them to expand beyond just the things where they have a rule based reward. And so now that since they have this new reasoning data, then they do sampling, take out the stuff that doesn't really fit well,
Mhm.
include a little bit of non reasoning data. But then they repeat the reinforcement learning process, but that allows them to have their own specific tasks that don't have a clear right or wrong answer. And the interesting thing is they're actually pretty loose with how they calculate that reward as well. They just take the summary at the bottom and then feed that into their own DeepSeek V3 to calculate a reward on like just how close was this generated summary to what we actually wanted in the output.
Yeah. Thank you. So the first 600, their RL samples now had 800K. That 600K are the reasoning samples, reasoning data, which is very easy to compute the rewards because most of them are math or coding or something that is very easy to evaluate, verify, and say you got the answer right or wrong. Then the 200K non-reasoning data, which you discussed, and when I looked at it, I didn't quite understand how are they computing the reward. And I think you mentioned they take the summary of that and they have another model to evaluate the reward.
Yeah, for helpfulness, we focus exclusively on the final summary,
Yes.
ensuring that the assessment emphasizes the utility and relevance to the response while minimizing interference with the underlying reasoning process. So, like at the end, it's probably like an additional, not quite like a regex, or maybe they do separate the thinking process to end with a summary, and then they use that summary at the end
Yeah.
to decide with this kind of, you know, looser,
Hmm.
non-rule based reward. And so how close is the summary to the actual, desired output?
Yeah. Yeah. That's the that's the part. Like, evaluating two texts are really hard. If it's a translation, I know how to evaluate translation. Summarization, sure. But here, do they have another metric? I wish they had shared a little bit more details on this.
Yeah, yeah, yeah. I mean, they're going with preference pair. Let's see, adopt a similar distribution of preference pairs and training prompts. Maybe they did use humans to decide like which one is the better.
Yeah.
It's not clear. It's not
Yeah.
exactly clear how they set up the reward for the you know the looser um,
Yeah.
responses. But
So then we get the okay. So we took a V3 base model, and then we, based on the R10, created cold start data set, sampled some examples, and post-edited with humans. That's our SFT data. Then we do the fine tuning. Then again apply RLGRTO method along with some extra constraint like language consistency, which was one of the problems. Then we have the newer version of R10, which they use to sample more data. Then they do again RL on this 800K data. So now I guess one step I was trying to understand is they had a R10 replacement that has a cold start. So they got rid of that model. They again started from scratch with the V3 model
yep.
and did RL on the 800K data. That's what they call R1. And now if we look at how does this model compare with competitors? R1 evaluation, I think it is doing pretty good. No surprise, it is doing better than the competition on maths because we saw they have so much expertise and they have their own data set. But overall, I think it is. This is the shocking moment for many people in the industry. Like, oh, okay, now we have a non-American company that is beating American companies.
I mean, it kind of speaks to how the constraints really force them to be to their force their ingenuity to be like to really come to light. Like
Yeah.
in V3, showing that you can, the intermediate steps and the feed forward model and just use a mixture of experts to kind of recover
Yeah.
the quality of a super powerful dense network. Like that was really impressive. You know, again, just for efficiency gains, let's take away the value model rather than
Yeah.
training two models side by side and we only actually care about one.
Yeah.
Just, approximate the advantage based off of the mean and the variance of the reward. Like that's wild.
I think that part somewhat sounds similar to MBR decoding that I've seen in machine translation. Don't quote me on this, but along that line where in translation, what we do when we generate outputs, we generate a bunch of hypotheses,
Yeah.
and then we reward an hypothesis that is the average of this sample. So that is usually
Mhm.
better. Something that is an average of the samples and best hypothesis we have generated. That is usually a better sample. In this case, I think they are along that direction, right? They generate a bunch of samples or hypotheses, and then they're computing the average of the group mean and the deviation.
Yeah.
Cool. So now we have a stronger R1 model that is competitive and sometimes beating the models from OpenAI and Anthropic, and it is definitely better than the DeepSeek V3 model. So this completes the section two parts out of three, right?
Yeah. Yeah. Then they go on to show distillation.
Yeah. So the
So
problem with this model is it's 671 billion parameters. It's huge, and only few people can run this. You the basic, 671 billion. Like we need a lot of RAM to host this. They do say you only need 37 billion activated parameters. That's the compute. You can get the output just by 37 billion parameters, but we need to keep 671 billion parameters in memory somewhere. Doesn't have to
Yeah.
be GPU memory, maybe on CPU memory, but you still need to have such big compute. So I can see why they went down to distill to smaller model. I think it's along the direction of the other models that we are seeing, like even OpenAI had O1 mini. They had O1 and O1. I'm not sure O1 mini is distillation, but I would like to believe it's a model that's distilled from O1. But again, I do not know the details about this OpenAI models. Okay, so I'm just trying to reach to the distillation experiment.
I think it's 2.4.
I skipped over that section.
Yeah. So this is interesting. They say that they take the 800K samples curated after step 2.3.2
Yeah.
and then just feed that into smaller models. But they don't give any additional information on how, if they do anything else to distill it. Like they don't say that the teacher model is, you know, they're not training on the probability distribution of the tokens because they may have a different tokenizer as the student model.
Yeah.
So they're actually just using the data set generated by step 3 or 2.3.2.
Yeah. So along this line, I think there was this paper called sequence level distillation. We usually, at least in theory, when we read ML books, distillation means you take the probability distribution of a parent model and try to match the distribution from the student model. But there was a paper, let me see if I can quickly find it. They said first, sorry, I think sequence level distillation. Basically, they're saying if you generate output sequence and then optimize for that, it's roughly similar
Hmm.
or maybe exactly the same. I'm not remembering the details. You don't necessarily have to. So this is 2016. Yeah, it's been a while. Yeah, this is from Alexander Ash. Cool. They basically say if you need additional convincing that instead of using the distributions from the parent model and matching the to match the distribution, you also need to match the vocabulary, right? The classes. So they say here that they show here that sequence level version seem to eliminate the need for um, actually I have to if I remember correctly, they say producing the outputs and then simply training on this or fine-tuning on the output is equivalent to you distilling and trying to match the probability distribution. That's why I think it's called sequence level distillation, is same as matching the probability. If I remember it correctly. Again, it's been a while. It's a 2016 paper. I have to refresh my memory. But that's something to read that follow paper. But I get your concern that can you just produce outputs and then fine tune the model? And is it really doing the right thing? I think.
Like, if that is the case, then it does lend credence to the concern of generating a data set from a competitor model. Uh,
Yeah. You cannot as a like anybody can distill now. You don't even need the whole probability distribution or vocabulary distribution, right? You just need outputs. And if you have outputs from your competitor's model, you can distill from it because of this method. But that's also where the legal terms, legal contracts get into the picture. Now, at least in the US, we know it's a nation of laws. There are so many regulations. If you could prove that your competitor distilled from you and your contract clearly says you cannot do this, like OpenAI models, I think they don't permit distilling, then you could sue them if the other company comes under the same law umbrella. But here, I think that's why some people were panicking. Now it's a Chinese company and it doesn't come under US regulation. Now, what can you do about it? This is why I think some people in media were panicking.
yeah, it's incredibly hard to prove,
Yeah.
and also the jurisdiction thing is a big deal. But
Yeah.
I think it's also I don't know if it's relatively necessarily common, like to when you're in the domain of making a, sometimes they call them SLMs, like a LLM that is like 16 billion parameters or less,
Yep.
basically operationalized LLMs that don't rely on the
Yep.
APIs, like a fine-tuned version of Llama, for example. Oftentimes those are fine-tuned using LoRa,
Yep.
a low-rank adaptation on top of the base model. And then you like generating, bootstrapping that initial data set, stepping away from the APIs towards a LoRa version of your model.
Mhm.
Like, where does that initial data come from? And then how do you expand it? So, I,
Yeah.
oh, it's a touchy subject when, like,
So
these
yeah.
LLMs like generally use like the entire internet to create their outputs a couple of years ago. Why doesn't it go back further to the people who generated, all the text on the internet? But anyway, I think we're getting a little off track with this.
Yeah. So I was actually able to run a few of these distillation models on my workstation I have here. So it's
Yeah.
amazing. I think there is this. Have you come across this software called Olama?
Yeah. Yeah.
It's nice. So I could just download and run some of these models. It's easy to install, it just runs. And even though it says, for instance, 32 billion, it takes far less than 32 GB. I think it's quantized, I believe, to 4 bits. I'll try running it and see if it works. I haven't downloaded that model yet.
Are you able to share your command line when you're doing it?
Sure, I think I downloaded some of this model. Let me see if I can switch my share screen window, click share. Yep. So see, I downloaded one of these models. I just don't remember which one exactly I did.
Do Llama LS? Llama LS?
Oh, yes.
This will tell you.
This is the one I ran, and it only took 9 GB. Oh yeah, okay, cool. So I'm just gonna see if it runs. Cool. So I have a GPU with 48 gigs, so it should be good. Anything you wanted to test? Yeah, this is basically I just wanted to see. It's very easy to run. I think it enables a lot of people to play locally with DeepSeek R1, and the license is so permissive that I'm sure there is a lot of startups, a lot of small companies which they couldn't afford or they couldn't explain spending millions of dollars now have access to these powerful models. And the performance, if you just look at the DeepSeek, so as I showed, here is a 14 billion model taking 9 GB and running comfortably under 10 or 11 GB RAM, and the performance of this model is not that bad. Can you remind me the table where they talk about? Yeah, this is the one, right? The one I was looking at. I think this one, 32 GB, 32 billion model, looks pretty promising. It can fit to most majority of the GPUs.
Yeah.
70 billion is even good, but this might require even bigger GPU. I would compare this with something like a O1 Mini.
Yeah.
Fair comparison, not with large models like O3 or O1. Yeah, these are cool, so we can use them. I think we are now reaching to the end.
Yeah. I mean, is there anything you would want to try after we got this paper down? What would you want to try as a machine learning engineer?
I would use these R1 models for many tasks, like whenever as an additional another model to try. Like currently, I'm trying with ChatGPT to try any coding problems. I go to ChatGPT and ask any math problem. I go ChatGPT and ask. But knowing this paper in depth and then looking at how their benchmarks are, especially for instance, see for some coding they are really good, and then for math also they're really good. I would use these models whenever I'm thinking of math problems or coding problems. I would add these. For instance, I think for coding, even OpenAI is still good in many domains, but these models are also very competitive. For instance, look at all their models. Look at as an engineer, I would always have coding, one or the other coding issue to take. There would be a bug I'm trying to resolve and I need second opinion. And here, when I look at the other models, they're so behind OpenAI. For instance, here you see 93 versus 20, but DeepSeek R1 is pretty competitive on this coding problem. So I would, as an end user, I would use this. And
Yeah.
as a researcher or ML engineer, I would maybe use them for distillation or producing more data if I want to produce. And we could distill from these models because the license, like we couldn't distill from OpenAI before
Right.
because of the licensing terms constraints. But here, OpenAI, DeepSeek R1 does not have those constraints. So yeah, those are my takes.
So for me, I mean, these models are dense models,
Yeah.
like the Quen model and the Llama model are dense models. I'm thinking it would be really interesting to try to enhance LoRa to work on the DeepSeek R1 mixture of experts. Yeah, 671 billion parameters is huge, but since
Yeah.
we're only activating 7 or 37 billion, let's just like cut out half of the experts and then bring it down to like 335 billion parameters in total.
Mhm.
Um, and then do LoRa, like an individual LoRa for each expert, and probably an updated routing set of routing weights for this particular LoRa task. There's a really cool open source library called Lorax, which allows you to Lorax, Lorax.
Right. Okay.
It allows you to have several LoRa models running on the same base model, all on a single GPU. So if you have LoRa, like LoRa's fine-tuned, all on the same base model, but for 5 different tasks, you could actually run all of those LoRa's on a single GPU, and then in your request, in your initial input, you specify which LoRa is actually the one adapting everything. And though all of them are running, the only ones that are actually modifying the hidden state
Mhm.
are for the request that you for the one that you actually requested to run. So if you could juice up LoRa to work on the mixture of experts for DeepSeek R1, then you could have a really powerful set of models if you're running it on Lorax. So
Yeah, then
that's
that would be
what I
cool.
would try.
So, but you're still talking about the full model, right? Full MOE
Yeah,
model.
yeah. I'm talking about like artificially, dropping some of the experts
Yeah.
and just saying, this is how much RAM I have. We're just gonna
Okay.
go with that.
So you're gonna
Uh,
prune some experts. I think they have some
Yeah, just
200 or
prune some
80.
experts, just they're gone,
They're gone.
and then do like a fine-grained LoRa on each of the experts. I think that would be a really cool thing to try.
Yeah, I think that's actually a really good idea. So in the DeepSeek, I didn't say the DeepSeek V3 paper. In the DeepSeek V3 paper, did they show if all experts are used like at that
No,
time?
no. So there's one X that's shared on
Yeah,
every token. And then they have like 256 other experts for each
yeah.
layer. And then they only use something like 4 or 16
Mm-hmm.
experts for each token. So if I just find out, like, I can, if I have a specific task and I characterize which experts are, like, what's the probability of calling each of these experts given
Yeah.
this task? I know they set it up so that it will generally distribute the work amongst these experts pretty evenly. But if for the tasks that I care about, like for a certain set of document understanding tasks,
Yeah.
these experts, I can get a probability distribution of how often these experts are called,
Yeah.
then I can just cut off the tail.
Oh yeah, I see. So the base model is trying to be universally good for every customer, right? Everybody on Earth. But maybe you don't care for everything. You just care about one specific domain, whatever you are working at your company. And then you probably don't need all those experts.
Exactly.
Maybe then you run on a validation set and assess which experts are used or triggered for this domain or this task. And
Hmm.
then you can just shrink.
Exactly.
And then, if you have some data, you could even do LoRa adaptations on those shanked model. That would be
Yeah, and
cool.
I would do lore on each specific expert, you know?
Okay. Yeah,
That's what I
that
would
would be
and
cool. I just
and then
want to mention. I think we are almost at 1 hour here.
yeah, yeah, yeah. We should stop soon. But
Yeah, yeah. So this is something cool I come across pretty recently, as you see, I think 2 days or 3 days ago. So this
Yeah.
is from NVIDIA themselves, NVIDIA blog. What they're doing is they're using R1 to iteratively, basically they're using R1 to write the CUDA kernel. And
That's
so this is cool. If you're writing code and then they set up this environment, the nice thing is, as we saw, most of their RL training was on something that is easy to verify, like math or coding. So here
right.
for CUDA kernels, they already have some implementation and they have test cases for it. So now you ask R1 to can it do better, much more faster. So it's easy to verify, right? Because they already have test cases. So they built this, and basically my takeaway is they are asking R1 to write better CUDA kernels, and then they benchmark it. Now they have much faster for some of these tasks, some of these operations. R1 can get you faster kernel than what they have.
It's kind of funny. It's like asking R1 to recreate those, what is it, PTX kernels that they wrote that are below CUDA. It's
Yeah,
like, can you write those kernels for me again? That'd be really cool.
yeah. It's like we know this is exactly what like most of them powered the R1, the creation of R1. Now asking R1 to it's like we humans evolved enough to now inspect ourselves and then can I know evolution gave me this part of the body, can I improve it?
Yeah. This is a
Um,
cool paper find. Yeah. Well, I think we came to a good stopping point.
yeah, yeah. So cool. So I think we may have to put some disclaimer. So at least I have to.
Yeah, yeah.
None of this is all these opinions are ours, and I don't represent. It doesn't represent our employer's opinions. We are just two old friends hanging out and chatting about tech. So this does not represent any of my employers.
Likewise, likewise. Honestly, this is just, getting back to the good old days when I was getting into machine learning under you, TG. This is fun. Let's do it
It
again.
was fun. It was 2016 or no, maybe 17 or 18 from the time.
Yeah. Yeah. Transformers had just dropped, and then look at us now.
Cool. We should do this more often. I don't know what will be our next paper. Maybe if we really like the RLs, we want to dive deep into RLs, we can take one of the either PPO or TRPO and dive deeper. That's one
Yeah.
direction. And quantization, we missed some quantization work in the V3.
What you like. I'm gonna see if I can see more about this distillation stuff. Like, I know some people are doing some work on model distillation with, or taking these distilled models and then going farther using reinforcement learning. So I'll see what I can find there, and then I'll share a paper with you.
Perfect. Yeah, distillation, quantization, or we can go deep. I think distillation, I also want to refresh my memory on that SQL for distillation. Then we can see that was 2016, almost like 9 years ago. Now we can see what are some new methods in distillation.
Yeah. Cool. Cool.
Right. Talk to you next time. Peace.
See you, man. Bye.